Hi. As a review, I have up here in part of our screen were some topics that we discussed in our last lecture. If you recall, in our last lecture, we began discussing the effects of lone pair of electrons on the central atom. And we said that if we have an electron domain geometry of AB3, we can derive an AB2E1, and that was sulfur dioxide. If we have an electron domain geometry of AB4, we can adopt an electron geometry of AB3E1 for ammonia, or AB2E2, which is represented by the water molecule. So today, we're going to be discussing the geometries in which the central atom may have an expanded octet, and we have a lone pair of electrons on the central atom. As you recall, in our last earlier lecture, we did introduce AB5 geometry for a situation in which we have a central atom surrounded by 5 bonded atoms. And we call this type of geometry trigonal bipyramidal. And I did bring my model with me, as you recall. This is the trigonal bipyramidal. So as you can see, we have a central atom. We have 2 atoms that sit on the axis. We call these our axial position. And we also have atoms that sit on the equatorial position. And we also address their bond angles, which are going to be important for today. Remember, when we have an axial to the equatorial, that's 90. It's 90 in any direction, and it would be 90 between the one on the bottom also. In the equatorial position, we have a 120-degree bond angle. And that's going to be helpful today to help us predict where we're going to put lone pair of electrons. As you recall in our discussion on the AB5 situation, where we have a central atom, has 5 bonded atoms and no lone pair, we introduced phosphorus pentachloride as our example molecule. And what we should recognize for PCl5, or a situation in which we have a central atom bonded to 5 other atoms and there's no lone pair of electrons, that our electron domain, there are 5 electron domains, 1, 2, 3, 4, 5 electron domains. And our electron domain geometry, as we've been stressing, is trigonal bipyramidal. And for situations where there's no lone pair, well, that tells us that the molecular geometry is the same as the electron domain geometry. It's trigonal bipyramidal. So what we're going to show in this part of our lecture is that we can derive 3 additional geometries from the AB5 model. We can derive an AB4E. That would be the situation in which we have the central atom, 4 bonded atoms. And what we're going to do is show that one of these can be a lone pair. And we can also have an AB3E2 and an AB2E3. Now, the big question that we have to address, and that's because there's different bond angles between the atoms regarding whether these lone pair that we're going to place are either at an axial position or an equatorial. So that's a big question that we need to address. Where are we going to put our lone pair of electrons? Well, would we like to put a lone pair at an axial position along the axis, such as we have this? Or are we going to put them along the equator? Because they are different. And the differences are due to the bond angles. What we find out that's most energetically favorable, and that's because of electron, lone pair, electron repulsion, is that we want to place the lone pair of electrons along an equatorial position. In other words, when we have a lone pair of electrons, the first spot we're going to put them is we're just going to pull one of our equatorial positions, and we're going to place a lone pair of electrons there. So that's the choice that we're going to make. And we're going to describe this geometry in a few seconds. This geometry that we're going to derive has a name to it, and it's related to a playground apparatus that you may be familiar with when you were a child. So we place lone pair of electrons along the equator. So the equator is the energetically preferred position for a lone pair of electrons. So let's go through an example molecule that experiences this geometry, and the name we're going to call it the seesaw. That's what we call it. So this is why it's called seesaw. I'll bring it back up. The seesaw, and we're putting a lone pair of electrons along the equator, and if we turn this upside down like this, we see that it looks like a seesaw. These two atoms are sitting along axial positions. The two remaining atoms that sit along the equator, we're flipping it, and the lone pair of electrons are going to sit up in this region. And the name of this geometry is seesaw. These two go back and forth. An example of a molecule that experiences this type of seesaw geometry, we'll call this seesaw, is sulfur tetrafluoride. So let's look at sulfur tetrafluoride, SF4. If we write the Lewis structure for this, we see that sulfur has 6 electrons. There are 4 fluorine. Each of them have 7. We have 34 electrons to work with, a central sulfur atom. All the fluorines would have their octets fulfilled. And we're left with 2 remaining electrons. And in this case, we're going to place those remaining electrons on sulfur because sulfur is an atom. Sulfur sits in period 3. Period 3 elements, when they're taking the central position, can have an expanded octet. So let's derive, first of all, how many electron domains, just so we can see this. How many electron domains? Well, just like we showed here for AB5, if we have an AB4E1, we still have around the central atom, 1, 2, 3, 4, we still have 5 electron domains. And the electron domain geometry is trigonal bipyramidal. That's the electron domain geometry. In other words, the way we think of the electron domain geometry, it's our framework of how regions where electrons are located like to distribute themselves around the central atom. So one of them is going to be a lone pair of electrons. So let's draw SF4 like we did for this situation. We have the central sulfur atom. We have 5 regions of electron density. And for SF4, 4 of them are going to be fluorine. 1, 2, 3, 4. Out here, we're going to put our lone pair, as we said, in the energetically favorable axial equatorial position. There's our lone pair of electrons. And if we look at sulfur tetrafluoride, we would see, as I have here, this is the situation that we have. We have a lone pair of electrons here. And if we put it in that direction, you could see, hopefully, the seesaw geometry that's adopted. So the molecular geometry is seesaw. Let's move one step further. Let's move one step further. I'm not going to give you an example molecule. But what if we take another lone pair? Here's our central. There's what we have right now. We have a lone pair here. This is AB4E1. What if we put another lone pair of electrons? Where would our other pair of lone pair of electrons? Our other lone pair of electrons also come off the equatorial position. If we have two lone pairs of electrons, this is shaped like a T. Maybe it doesn't look that well, but you can get the idea. That's a T-shaped molecule. So if we have AB3E2, we have a central atom A, and we end up with a T-shaped molecule. Now, if we placed another lone pair of electrons, once again, they would come off of the equatorial position. And this is AB2E3. And for this geometry, this molecular geometry, we have a linear molecule. So these are examples of how we can derive different molecular geometries from a generalized electron domain geometry. The last molecule type of geometry we're going to look at is that's derived from an AB6. As you recall from our lecture that we did on Friday, AB6 is a geometry in which we have a central atom A, and it's surrounded by 6 atoms B, and we have 6 electron domains. All bond angles are 90. Everywhere is equivalent. These are all equivalent spots on this particular molecule. So we don't have to be careful of where we put a lone pair, and that's important. This has an electron domain geometry. And since all electron domains are involved in bonding, it also has a molecular geometry that are both the same as we have been discussing. These are octahedral. And we can derive several geometries from the AB6. We can have AB5, E1, AB4, E2, AB3, E3, AB2, E4. And remember, notice that all these little subscripts add up to what we started out with. And these are just simply placing lone pairs of electrons wherever we want. So let's look at a situation in which we're going to produce an AB5E1 on a particular molecule. I'm going to do AB4E2 because I wanted to address how noble gases actually interact in these expanded octets, because noble gases do, in some cases, have been observed to create molecular compounds. So let's look at, I'll just give you the name. AB5E1 is square pyramidal. And this would be the case in which we would place a lone pair of electrons in one position. That would be an example of a square pyramidal. It creates a pyramid that has a square base to it. And it has a lone pair of electrons. You can see I'm putting my lone pair of electrons there on the bottom. Let's look at xenon tetrafluoride. Now, xenon is an inert gas, and this is also leading to the theory behind the expanded octet, that there's additional space, d orbitals available. Both of these are valid reasons for accepting that noble gases do form molecular compounds. So in this case, xenon has 8 electrons, and there are 4 fluorine. 4 times 7 is 28. We have 36 electrons to work with. In this case, we would have our central xenon, and we would have 4 fluorine. And each fluorine would have a complete octet. And we would see now that we've used up 8, 16, 32 electrons. And we have 4 electrons left over, and we're going to give those to xenon. And let's recognize that xenon has 6 electron domains about it. So the electron domain geometry would be just like we've drawn here. This has an electron domain geometry. Octahedral. And that's because this case, the central xenon atom has 6 electron domains about them, and they would distribute themselves in an octahedral fashion about the central xenon atom. So let's look at our model here, and let's put xenon in the center. This is what we're seeing. We have xenon here. And where we're going to put our fluorine, we're going to put a fluorine out here, a fluorine there, and a fluorine there. And our lone pair of electrons, we're going to put them as far away from each other as possible. Now, when we start to put a second pair of lone pair of electrons, we're going to distribute them completely opposite of where the first pair were. In this case, we're going to have a lone pair of electrons above the plane and below the plane. And what we end up with is, if we look down on this molecule from above, we see that we have, just as I've drawn here, a square planar molecular geometry. And in this situation, all bond angles would be at 90 degrees. And that's the type of geometry we get for AB4E2. Now, if we had an additional lone pair of electrons, we're going to once again end up with a somewhat of a T-shaped. And AB2E4, those are going to be linear. So I have a table. I have a table with all these geometries as a summary listed on today's PowerPoint. We've gone through all the different arrangements of how we can use our electron domain geometries to derive molecular geometries when we have lone pairs of electrons on the central atom. And that's where we're going to end for exam 2. You should be able to predict a geometry for any type of molecule or polyatomic ion. Let's do 2 examples on today's discussion. Let's show how we can use the information that we've discussed up to this point, and this is a topic that's covered in 5.9. We should now be able to VSEPR geometry. We're going to make some predictions using everything that we've learned up to this point. Let's look at 2 molecules. And let's predict a VSEPR geometry. So when we're predicting a VSEPR geometry, we do have a certain set of rules that we always follow. The first thing that we need is we need to write a Lewis structure. So we have sulfur. Sulfur is a group 6A main group element, and it has 6 valence electrons. There's 2 fluorine, being in group 7A, they have 14 total valence electrons for the 2 fluorine. So to build our structure, our molecule, our Lewis structure, we're going to work with 20 electrons. Let's put sulfur in the center and surround it by our 2 fluorine. And let's fulfill the octets of the surrounding fluorine. And let's count how many electrons we've used so far. 2, 4, 6, 8, 10, 12, 14, 16. We've used 16 electrons. We have 4 electrons remaining, and we're going to put these on our central sulfur. And let's answer some questions about this molecule. First of all, what's the electron domain geometry? In other words, how do the regions of electron density about the central sulfur atom, how would you expect them to arrange themselves? Well, there are 4 regions around the central sulfur. So let's get rid of all of our data. Here's sulfur. And we have 4 regions about the central. 1, 2, 3, 4. So remember, when there's 4 regions of electron density, or 4 electron domains is another way of saying it, around a central atom, we're going to predict that the electron domain geometry is tetrahedral. And understanding about the electron domain geometry will help us derive the molecular geometry. Notice 2 of these regions are lone pair of electrons. And 2 of them have fluorine. So what type of molecular geometry would you expect for this situation? And remember, oftentimes you can think about other molecules that we've addressed. So this, in essence, is what we call A, B, 2, E2. And as you remember, hopefully, this was what we derived for water. AB2E2 is a bent molecule. So this would have a molecular geometry in which we have a sulfur with 2 fluorine and 2 lone pair of electrons about the sulfur atom. And this would have a geometry that would be described as being bent, very similar to the geometry that we derived for water in our last lecture. Let's try another example. Phosphorus tribromide. So let's take into account our valence electrons. Phosphorus has 5, 3 bromine, each of them have 7. We have 26 electrons to work with. Phosphorus, and here's our 3 bromine, and we have a single bond about them. And we would fulfill the octets. And we would see at this point we've used up 24 electrons. And we have 2 electrons remaining. And once again, we would predict in this situation that we have 4 electron domains about phosphorus. Three of them have bromine, and 1 is a lone pair. So the first question we might ask, what's the electron domain geometry? So the electron domain geometry is once again tetrahedral. And that's because our central phosphorus atom has 1, 2, 3, 4 regions of electron density about it. 3 of them are involved in bonding. So this is an example of an AB3 E1, which is quite similar to NH3. And we would expect this geometry, the molecular geometry, trigonal, pyramidal. Let's try another one. This is one I had in an earlier slide, but I didn't go over, but I'll go over this one. And the reason why I'm going to go over this is because the formula is quite similar. Okay, so we just did PBr3 and said that it's trigonal pyramidal. That's its molecular geometry. Let's try chlorine trifluoride. Notice, very similar formula. So you might say, oh, it's probably going to have the same geometry. Can you make that assumption? You cannot. You cannot look at it and say they have the same formula. They're probably going to have the same geometry. we need to write the Lewis structure as a first step. So let's write the Lewis structure. Chlorine provides 7 valence electrons, 3 fluorine, 21. And we have 28 electrons to work with in this case. Chlorine sits in the center, and we're surrounded by 3 fluorine. And let's fulfill the octets of all of our fluorines. And we would see at this point we've used 24 electrons up. Four electrons remain, and those 4 electrons are going to be given to the central chlorine atom. First question, what's the electron domain geometry? What's the electron domain geometry? And that is really big in understanding the difference in the geometry between phosphorus tribromide and chlorine trifluoride. Even though their formulas are quite similar, they're identical in many cases, one central atom with 3 surrounding atoms, their electron domain geometries are going to be different. Chlorine sits in the center, and we have 1, 2, 3, 4, 5. 5 regions of electron density about that central chlorine. 2 of them are going to be lone pair of electrons. So remember what we said about this type of electron domain geometry. This is trigonal bipyramidal. Where do lone pair of electrons want to be placed at? The lone pair of electrons want to be placed on equatorial positions. In other words, I'm just going to erase. There's going to be a lone pair here and a lone pair there. And we're going to put our fluorine. And what we're going to do is we're going to erase the lone pair of electrons, because when we look at a molecular geometry, we don't want to focus on lone pair of electrons. We want to focus on the atoms. What shape is that molecular geometry? It's T-shaped. So notice, similar formulas, different molecular geometries, because we're building the molecules from different electron domains, types of geometries. That's an important take-home message. And that's it for exam 2. Our next lecture will be on Wednesday, which will start topics that will be covered on our 3rd exam.